Welcome back to Muddy Math, where we take middle school math concepts that are a little muddy and clear them up. Today is day 17. I hope I'm not making you dizzy. Day 17 of our 28 Days to Phi. I'm so lucky. I have a new camcorder. My dad bought it for us so that we can improve the quality of these videos for you. I am doing some minor adjustments. So as I adjust, I welcome you to get adjusted. Good morning. Good morning. Okay, so today's details. What are we going to do with these details? We need to find out what details will help us in the journey to finding phi. What details can we take from this week's learnings and help us find phi and be creative with phi? Okay, so there we are. So this is a learning process for everyone. I'm really grateful for all of your patience, trying to get this right for you, make this 30 minutes exactly what you need. Okay, whew. Here we are, day 17, details. So to get started today, let us take a look at the activator. So I want to show you that this process of you finding phi is an invitation to explore your interests and think of things creatively. And so some things that I'm learning is how to use a camcorder to do live streams. So learning, thank you. I'm so excited to be on this journey with you and be humble and have humility with you all, realizing that I don't know everything and nobody does, and that the more we can empower you to break through the edges of your understanding, the better off our entire world will be. So anyway, here I have learned how to bring my cursor onto my screen. So, I celebrate these little moments of learning how to use a camcorder and learning how to use a cursor. So here's our activator. If you downloaded the PDF Enhancement, you'll see that the activator has the same questions as yesterday. How many branches do you see? How has nature impacted your learning? And how tall is the tree that I am looking at? So I'm going to go ahead and switch off of the view that allows me to use the cursor. But what I want you to see here is that this tree is the one I want you to estimate the height of. And if you look, it has a beautiful phi. I found phi, a phi find. The branches of this tree are truly incredible. They're beautiful. Okay, and this is me standing next to the tree at the base. Okay, this is on my hike where I go outside to learn about math, to find phi, to be inspired by nature. So our activator is very open. There's no wrong answer. There are multiple right answers, and you can choose which question you want to focus on. Please grab a friend. Please grab a mirror. Please grab a selfie device of some sorts. And I want you to discuss, how many branches do you see? How many branches do you see? How has nature impacted your learning, or how tall is the tree that I'm looking at? So I'm going to go ahead and put my face back on. Okay, and bring sort of a still of the activator. So there you are. How many branches do you see, or how tall do you think that tree is? And here I am. Okay. There. Okay. So using scale, okay, those two photos were taken the same distance away from the tree. You can see that the trunk is relatively the same size in both images. So I would say that maybe that tree is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 of me. What do you think? Do you think more or less? So if I am 5'7", 5'8", 5'8". So let's just round that up to 6 feet, because in this scale, it doesn't really matter, like, those inches don't matter. It's a huge tree. So we've talked about in the past, how humans have a margin of error. And so in this case, to estimate the height of a tree, we don't have to worry about those inches. So say I'm 6 feet tall, there's 14 of me. Let's do a little number talk to get started here. What would 14 times 6 be? How would you do that? Would you add 6 to itself 14 times? Can you think of 3 different ways to get the product of 14 times 6? You know me, I like to break it into its place value. So 14 times 6, I'm going to think 4 times 6 and 10 times 6. So 4 times 6, 24, and then 10 times 6 is 60. 10 times 6 is 60. 4 times 6 is 24. How can I get the product with those two numbers? 84. Does that make sense to you? Did you get 84? How else could we do it? Could we do 15 times 6 and then subtract 6 away to get 14 times 6? So 15 times 6 is 90. I know that because 15 times 2 is 30, and then multiply that by 3 because 2 times 3 is 6, so 30 times 3 is 90, and then I take away that extra 6 to get back to 84. How did you do your number talk this morning? Can you do it multiple ways? And again, thank you. I'm so excited to use this new equipment, and I'm learning. So I hope you see that learning is a journey, and to embrace the struggle moments is the point where you break through the edge of your understanding and really create strong synapses and pave the way for neural pathways. So let's go ahead and get started today looking at the details. We want to look at the details of a pyramid to help us understand phi a little bit better. So if you, that's a good way I could do it. All right. So if you were able to look at the enhancement for day 16 yesterday, you would have seen that we constructed a beautiful three-dimensional model, a 3D proportional model of phi. A 3D model of phi using the Pyramid of Giza. So this is a 3D model of the Pyramid of Giza. How cool is that? And a cross section is when we slice something. If I took a knife or something flat, okay, and I sliced this, slice, chop it off, okay, we would lose this whole front part. Let's go ahead and do that. Let's actually slice this pyramid. So, cross sections are 2D shapes formed by slicing a 3D solid and looking at the 2D stamp that the face would make. So I'm going to go ahead and cut this, right? So if we were to slice this pyramid through the apex, where the apex is perpendicular to the base, the slice is going to be perpendicular to the base, I'm going to be cutting right along those lines. So I'm going to go ahead and adjust the camera so that I can just be straight ahead of the camera, and we'll be all good here. I'm going to bring this to the right so you can see it. Learning is beautiful. That's much better. Okay, so a cross section of a 3D solid, and I can stand up straight and go straight in front of the camera. is when we take a two-dimensional plane and slice a 3D solid. Okay? So I'm going to cut perpendicular to the base, through the apex, through the center of the base, right? We made that circle on the bottom of our base, through the center of the circle, right? The center of the circle is right below the apex of the pyramid. So I'm cutting this because I'm imagining that I'm slicing this pyramid into two equal halves. And when I slice a pyramid, okay, a 3D solid, a cross-section is asking you to think about what is the two-dimensional stamp. Like if we were to take the pyramid, now that we sliced it and stamped, what would we create? What two-dimensional shape will we create? And we would create this isosceles triangle. So that is the cross-section of the Pyramid of Giza. Okay? See if you can try that on your own. I really hope that you all had time to make a 3D model of the Pyramid of Giza, whether it's with Play-Doh or paper, you know, whatever. Check out the Day 16 video supplement so that you can go kind of slowly with Sam to creating that. Also, the Day 16 gives you the mathematics to create it. But any pyramid will do, even if you don't have a scale model of the Pyramid of Giza. You can just make any square pyramid. So make a square, make 4 isosceles triangles, and make a net, and then build it. Or make it out of Play-Doh, or pizza dough, or whatever. Okay, so next we want to measure a solid. Measure a solid two-dimensionally in square units with surface area and cross-sections. So that's saying taking the net, right, so we learned this is half of the net of the pyramid, we cut it in half. So when we look at the net of a 3D object, that gives us the surface area. How many square units tile the net of a 3D object? And this is not for cones and, well, cones would work, but spheres and oval, like egg shapes, those we can't lay flat. So that's a whole nother sort of tangent. So if you're interested in that, I encourage you to explore, you know, looking at the maps of the world and seeing how they flatten it out. How do you flatten out a sphere or an egg shape? Just a tangent for you all. But let's get back to our 3D solids that are comprised of polygons, right? So polygons really allow us to lay it flat. So two-dimensionality is measuring the area of the net, the surface area of the 3D object, and then we can also look at two-dimensionality of a 3D solid by analyzing that cross-section. So here you see that this is the cross-section of the Pyramid of Giza through the apex perpendicular to the base. Okay, this is our little cross-section of the Pyramid of Giza. So the cross-section, one cross-section we can create is an isosceles triangle. There are so many other cross-sections of a pyramid, and I encourage you to try to find them all. How many are there? What do you think? How many possible 1 or 2 or 0, 1 or 2 dimensional objects, geometric objects, can we make from slicing a square pyramid? I think I'll make a supplemental video for that today for you all. What are all the cross-sections of a square pyramid? So before that gets uploaded, I challenge you to find all the cross-sections you can find of a square pyramid and see what I post later and see where our perspectives are the same and where our perspectives are different. Okay, and then volume is deciding how many cubic units fill this pyramid. So the cool thing right now is that we have, you know, a little dish made out of half of a pyramid. So this is half the volume of the pyramid, right? Half the volume of the pyramid. So if I were to fill this pyramid up with little cubes, fill it in, how many cubes would fit? Now you're saying, well, it's not meeting at a right angle, so it's not going to fill perfectly with cubes. It's not going to do that, right? Because a cube's not going to sit nice in that corner that's not a right angle. So that's where it gets a little bit more complicated with pyramids versus things like this. My yoga block, okay? My yoga block, I could fill up with little cubes because it all meets at right angles. So this would fill up with little cubes. But my pyramid, I'm going to have to think a little bit harder because I can't possibly fill this up with little cubes because the cubes won't fit in these little, these corners of the pyramid. So volume is measuring in cubic units and surface area is in square units. And we can, of course, measure the cross-section in square units if we wanted to. Okay, let's continue on. Formulas. These are the formulas that help us find the details. Fine-tune the details, attend to precision. Like I said, we can't just naturally fill this pyramid up with cubes, so that's where we resort to formulas that have been already discovered for us, and we can implement those to calculate different measurements like surface area, volume, and more. So these are all measured in square units and cubic units. Single units in the first dimension are things like height, right? Height is measured in a single unit in one dimension, one direction. Square units tile a surface, they go in two directions. So if you were to make a little square, a square is something that you can tile with, right? If you slide your feet on the floor, you're tiling the floor. And then when you spread your feet and your arms all around, that's volume, that's cubic, it's 3 dimensions. Up, down, sideways, back, forth, right? Those are 3 dimensions. If my feet are stuck to the floor, okay, then I'm not going to, here, now we have a camcorder, I can show you, right? So when I slide my feet around, I'm only going left and right and forward and back, okay? I'm not going up and down because I'm measuring the floor in 2 dimensions. It's a flat surface, that's square units. Okay, the space in the rooms that we are all occupying, okay, the space in our rooms is 3-dimensional. And then a line is 1-dimensional. So these are really important things for you to get some spatial reasoning when we're starting to talk about formulas and inputting different values into formulas to create measurements that help us understand objects. So again, we're assigning values to geometry so that we can make sense of them and communicate better, right? So without further ado, okay, let's make some calculations with the Pyramid of Giza. So let's find, what do you think the Egyptians would actually want to know? Do you think they'd be more interested in the surface area of the Pyramid of Giza? Okay, do you think that they are more interested in painting? Did they paint the pyramids? Did they need to wrap the pyramid up in a gift? Did they need to shine the pyramid? Did they need the surface area? Or do you think they need the volume? What do you think is more important for the Egyptians back in the day? What was more important to them? How much stuff they could fit in the pyramid? This is a triangular pyramid, but I dropped my other one. Or do you think they're more concerned with what goes around the pyramid? I think nowadays, if they're restoring these great pyramids, they might want to know the surface area to know how much restorative material they need. But in terms of when the ancient Egyptians built the pyramids, I personally think they're more concerned about what can fit inside. So let's start off with finding the volume of the ancient Pyramid of Giza using our single unit compared to phi. So we're not actually using the actual measurements of the Pyramid of Giza, which is in the hundreds. We're just going to use approximations of phi and our unit of measure 1, which we've determined to be the distance from the center of the base of the pyramid to the outside edge of the pyramid, meeting at a right angle. So what you need is a pencil and a piece of paper, and you need this enhancement PDF showing you the formulas to pay attention to in determining volume for a square pyramid. Okay, so let's start fresh so we all can kind of start at the same place. Those were all of our notes from yesterday, day 16, wrap. Thinking about how we could wrap up objects in a net of proportional to the Pyramid of Giza. So today we're going to calculate the volume of the Pyramid of Giza. Okay, the formula for volume, if you look on the PDF enhancement, so I'm going to bring myself to the front so that we can see more. And then I'll also bring the PDF up, but I'll make it smaller so that you can see it as a reference. So the volume of a rectangular prism is length times width, so times height. So I'm drawing a little rectangular prism. A rectangular prism is like my yoga block, right? This is a rectangular prism because it has two bases that are parallel to each other, and then those bases are rectangles, and there's no apex. These are lateral faces that connect to the bases parallel to their opposites because it's a rectangle, but more importantly, the height of the prism is perpendicular to the two bases. So these are the four faces, and these are the two bases. This is a rectangular prism. So for a rectangular prism, all we need is length times width times height. Okay? For the volume of a square pyramid, okay, the volume of a square pyramid is a third of length times width times height. Wouldn't it have been cool to be the first one to figure that out? I challenge you. Build a square pyramid. Build the rectangular prism with the same square base. Fill them up with grains of rice or things that you have in your kitchen. Something that you can, that's small enough to fill in those tight corners, but big enough that you're not creating a huge mess. Like flour might not be great with a paper model, but notice that when you fill up your pyramid, and then you can use 3 of those to fill up the rectangular prism. That might also be a video supplement coming to you this weekend, okay, when we don't have live streams, but you can still tune into Muddy Math to explore the edges of your understanding and break through and learn. Okay, so the difference is that this formula it reads different when you look at it on like a formula page. You'll see it as 1/3 big B base times the height. So if you notice that big B corresponds to length times width, if we're using the expression defined for the volume of a rectangular prism. So the idea there is that we have a rectangular prism, so we have a square base, because a square is a rectangle, but not all rectangles are square. So that's a square base. And then it goes straight up with a height. Okay, remember our base has a radius of 1, so that this length is 2, this length is 2, okay, and then the height of our pyramid is the square root of 5, right? So once we have the height that we want, we can connect those dotted lines again to form our top base. The bases of a prism have to be parallel to each other. So here is our rectangular prism that is 3 times larger than our model of the Pyramid of Giza. So if I recreate that drawing for our Pyramid of Giza, okay, there's our square base with radius 1 and side lengths 2, and then up the apex is the square root of 5. But instead of creating a parallel base, oh, you can't see. Hey-oh! Hey-oh! See, this is what I miss my students, because they'd be like, Miss Flynn, we can't see it. We can't see it. All right. So then we bring the vertices of the base up to the apex, which is at a height of 5, okay? And we know that the slant height here is, the height of square root of 5, we know that the slant height here is the slant height here is 5, okay? And there's that right triangle we've been playing with a lot lately. So the fact of the matter is the volume of our model of the Pyramid of Giza is a third of the volume of the rectangular prism formed with the same height and the same base. So the volume of our rectangular prism is 2, which is the length, times 2, which is the width, times the square root of 5, which is the height. Okay, so let's come over here. Okay, so we have 2 times 2, which is the base, times the square root of 5, which is 4 root 5. Now, this is an irrational numeric expression because we have an approximation for the square root of 5. Does anybody remember what that is? What number times itself makes 1.618? If I remember correctly, which my memory is not great, it's 1.27, but let's just double check and see because I have a tool, woo, here I am, that I love, okay? So I'm going to remember the irrational approximation of phi is the square root of 5 plus 1 divided by 2. Oh, go to syntax error. I had one too many parentheses. So I have 1.618. You can't really see that well because it's focused on the back. Now I can do the square root of that. Second answer takes the answer from the previous expression and 1.27. So I was right. Okay, so the square root of phi is approximately 1.27, so we have 4 times 1.27, and then that's going to be about a quarter of 4, a quarter to 4, a quarter of 4 is 1, so I'm saying this should be close to 5. 1 1/4 of 4 should be close to 5, but let's see. So let's multiply 4 times 1.27, and what do we get? Oh yeah, oh yeah, 508. Approximately equal to 5.08. So what we should get is that this, okay, is a third of that value because the volume of a pyramid is a third of a prism with the same area base and the same height, okay? So we know that the length times the width times the height of our pyramid is 2 times the square root of 5. So I know that this will be multiplied by the area of the base times the height of the pyramid, okay? And we know that the area of the base is approximately equal to 5. And I'm just going to round it to 5 because we talked about the human error component and we're rounding anyway. So then 5, what's a third of 5? Equals 5/3, which is equal to 1 2/3, which is approximately equal to 1.67. Okay? The last thing we need is our units. We're measuring volumes, so it's cubic units. Yes, it's the space that occupies the room. Cubic units, okay? So we need to write units cubed. Okay. Now, if we had the scale factor of how many times our little model fit into the actual Pyramid of Giza, all we would have to do is take that scale factor and multiply our calculations, our measurements by that to figure out what the actual volume of the Pyramid of Giza is. So can you figure that out? Can you determine the actual volume of the Pyramid of Giza? Why don't you do it with our scale model and then compare it to what you would do if you actually measured the Pyramid of Giza? And the Pyramid of Giza's measurements are available online, so I encourage you to be curious and find that out for yourself. So because of my technical wrestling in the beginning of class, I lost a couple minutes and we're at 10 o'clock, but I just still want to leave you with the closure for today. So let me bring that back to the foreground. A square pyramid, this just gives you some context if you're interested in thinking about that. But what I really want you to do, which is going to help us think about tools and will maybe be another video supplement, is the bottom right question. How could the Egyptians use rope and right triangles to build the Great Pyramid of Giza? So how, like, all of this, how could they have done this? Think about the tools that Egyptians had back in the day, right? Another, if you're less interested in history and you'd rather close off with how does the slice compare to the faces of the pyramid, that question is referring to comparing and contrasting the isosceles triangle on the face of a pyramid versus the isosceles triangle that's the slice of the pyramid, right? So could you compare and contrast those? What do you notice? Or how do you think Egyptians used rope and right triangles to build such a magnificent, awe-inspiring structure with this very basic tools that they had in ancient Egypt? They didn't have bulldozers and cranes. How did they do it? Well, it's been a pleasure. I really miss your faces. Even if I don't know you and you're following along on this journey, I miss you too. Stay smiling, stay talking to each other, stay active, stay happy, stay home. And my heart is so warm for you. Be proud of yourself. If you want to do a little power pose today, like the ancient Egyptians must have done when they were moving those big blocks for the pyramids. You're amazing. Smile. You're worth it. Engage with mathematics. It will make this whole world a better and happier place if you do it. Signing off, Sam.